Hi, my name is Przemek Chojecki and I'm a co-founder of Board Technology, a company specializing in quantum computing. And in this episode, I wanted to tell you more about what is quantum computing, what we do exactly, what's the future for quantum, and why it's exciting to be in this area right now. So starting with this, basically what we do is we try to do software on different quantum devices that are currently available. You might have heard about D-Wave systems. There's also Rigetti, IBM, Google, Microsoft are trying to make their own quantum devices, and there are actually many more companies like that who are trying to build their own quantum device. So right now, what's happening is that you will have noisy devices which are not perfect and definitely are not yet available for commercial use, or maybe they are available for commercial use like D-Wave or Rigetti. They have their own cloud platform, but actually the results you're getting are not still commercially applicable. They are suboptimal. They are worse than what you would get using just machine learning and classical computers. So why you should bother? Why quantum computers? So to start with that, you probably should know that Moore's law is coming to an end. So this doubling of speed of transistors of computers in general is coming to an end because basically those transistors and those chips, those processors are getting smaller and smaller, and we're at the verge of being able to still make them and to not defy some physics law. So that's why people are looking into different sources of computing. And quantum computing is one of them because quantum computing is at the micro scale. And basically you're trying to use the force of quantum physics. So instead of having bits like 0 and 1, you have actually quantum bits. So 0 and 1 and 0 and 1 all together. This is the superposition that you're using in quantum bits. And this superposition is allowing you to actually go much faster or much deeper into the solution tree. So you might imagine that classical computers are tackling problems and finding solutions one by one. They go straight. And actually, quantum computers, the whole idea is that they go and try to find all the solutions at once. So that's a completely different paradigm. That's why it's completely different way to program them, even though it's very similar to what you might know from the classical computers. You still have frameworks around Python, like PyQuil, tools that you try to, which you can try to program Rigetti. That's one of the languages that is used, but it's still basically Python plus a little bit knowledge of quantum physics. So if you know data science, then by learning a little bit of quantum physics, you can go into being a quantum data scientist, basically. But why bother? So basically, quantum bits are also they're in superposition plus they're entangled all together. And this entanglement actually allows you to build computing power exponentially on the number of qubits. So classical computers gives you linear power in terms of number of bits you're having. Quantum computers will give you exponential power in the number of qubits. And that's a big deal. That's why quantum is getting right now a lot of press, because in the end that might solve this problem with Moore's law and getting access to more computing power. So that's why quantum computing is important. We're still not at the stage. A lot of happened, however, recently, especially in the last 2 years. You had really many breakthroughs in this area. There are many devices available right now with real use applications. So you might have heard jokes a couple of years ago about how quantum computers are finally able to multiply 2 by 3. This is not the case anymore. You're able to get much more complicated results. To give you an example, basically, I think 2 years ago, Volkswagen, in partnership with D-Wave, actually were able to optimize routes of taxis in Beijing from the city to the airport. So something real, which is a real world problem and has real application. And this also allows you to think that quantum computers might bring a lot of computing power to problems that currently are intractable, like finding new drugs, like optimization problems, really complex optimization problems. So what we do at Bohr Technology is basically we looking at all these quantum devices from D-Wave to Rigetti to IBM, Xanadu, and actually trying to solve optimization problems like traveling salesman problem, vehicle routing problem, mostly in transportation and logistics, but we're looking much broader than that, and we're thinking about optimization problems that we might solve using quantum computing. So for now, because those devices are still imperfect, what we are getting is maybe not better or faster solution, but actually different point of view, which is also very important because those kind of problems that we try to tackle are so complicated that you're basically not able to use classical computers in order to solve them. So any kind of insight which is different from classical computers is valuable. So at this point, we're basically solving different logistics and transportation problems, also related to autonomous vehicles or predictions. So a big part of the story is also research that we need to do. So around Bohr we have the whole BQ ecosystem program, as we call it, and this program is trying to get as many people on board. So if you're interested in programming quantum computing, go on our website and check it. We're basically trying to get as many people to quantum computing as possible because we believe that to really have the next level of breakthroughs, you would need much more talent in the pool. And for now, it's still very early stage, like basically like 60s in classical computing when you have those big machines, and that was the very beginning. So we're still at this stage when nobody really knows where it's all going to end and like where we're heading, like where we'll get this to the level of quantum advantage or quantum supremacy. So the point where quantum computers will be able to overcome classical computers, at least in certain tasks, because quantum computers are like very precise calculators, but in very niche problems. So it's sometimes very tricky to really get a good solution for a problem because of the probabilistic nature. That's something completely different from classical computers. And interpreting those results is also a task in itself, and like overcoming the noise, that's a hard problem. So in a quantum computing community, we need much more people to actually tackle those problems because it seems like you need still a couple of breakthroughs to put it on the level that it will be commercially available. Hopefully with the current state, it seems like we're going in a good direction, and definitely within like 2 or 3 years, we should be able to get to the level where it's absolutely clear to anybody that quantum computing is the way to go. So this is it. I hope this was helpful for you. If you have any feedback to add, you can write me an email, find me on LinkedIn, or just comment below. Thank you. Hey.